All right, so when we're dealing with energy, we do have this convenience of, I have an initial condition, final, yes?
Do we have school on November 5th?
Why wouldn't we?
Because I think I showed up on the calendar that we didn't have school, but I could be wrong. I don't know if it's just because of election day or something.
I don't think we can have election day off.
Take it.
But we'll shift if we find out that that's incorrect. So when we're dealing with energy, initial final condition, in the absence of any non-conservative work, we have energy is conserved, which is really convenient, especially in high energy physics where there are no non-conservative forces. Because you're dealing at the particle level, energy conservation is an incredibly powerful tool. Unfortunately, we lose information. We lose direction in it because we're dealing with scalars there. So let's take another situation. I have two objects. I have object A and object B. By Newton's third law, the force on A from object B should be the negative of the force on B from object A. The negative just indicating the opposite direction. Now the two objects will touch each other for the same, or interact, they don't actually have to touch, but they will interact for the same amount of time, that A will touch B for as long as B touches A. So what I'm going to do is I'm just going to multiply both sides by the time that they're touching each other. So this is Newton's third law. That we just multiply by time. For Newton's second law, what is force equal?
MA?
Yeah. So this would be the mass of A times the acceleration of A times time is equal to the negative mass of B times the acceleration of B times time. What is acceleration times time? Okay. Or?
Oh, I get it now. That's my joke. Acceleration.
Over here. What is acceleration?
Like, what is it? Centripetal or change of velocity? Change of velocity over time.
Yeah.
Oh, so
It's
just.
the change in velocity over time. So what would acceleration times time be besides at?
Change of velocity.
Yes. So this is mass of A times the change in velocity of A is equal to the negative mass of B times the change in velocity of B. So that's just mass of A times VA final minus VA initial equals negative mass of B times VB final minus VA final. If we distribute, I get mass of A VA final minus mass of A VA initial equals negative mass of B VB final plus mass of B B, oops, that should be a B there. Should be B initial. Mass of B B B initial. That's a pain.
Mm-hmm.
Be nice if we had some nicer way of doing this. Let's simplify it a little bit, just so we don't have to write as much. I have MV showing up 4 different times, so it'd be nice if I just had a single letter to represent MV. So I'm going to choose P.
Does that have any reason? Or is that just a letter? Is that gonna have a reason later?
Oh, why we're choosing P?
Yes.
Tradition.
Tradition.
Yeah,
That's
I actually have heard why the letter P was chosen, but I can't remember what it is.
Okay.
And I've seen some videos where they go, hey, why are we using the letter P? But I have heard, I just can't find it again. It's one of those mysteries. So if I let P equal MV, my equation down there just becomes PA final minus PA initial, and they are still vectors, is equal to negative PB final plus PB initial. Now, at this point, there are 2 paths to take. I'm going to just briefly take down one path, and then we'll come back to it. This is just the final minus the initial of something. That's just delta PA. And over here, this would be negative delta PB, whatever P is, besides MV. So just sort of tuck that away for a moment, and let's come back over here to this equation. What I want to do is I want to get all the initials on one side and all the finals on the other. So I'm going to take the PA initial, add it to both sides, and the PB final, add it to both sides. So I have PA final plus PB final is equal to PA initial plus PB initial. So whatever P is, if I add up all the values initially, that's going to be equal to the total finally, or the final total. So I could just write this as P initial is equal to P final. This is the kind of thing that makes physicist hearts go off on Twitter. Because we have this value here of P such that my initial value is the same as my final value. It is a conservation law. Now, of course, we can't just go around talking about conservation of P. We have to give it a different name, and P stands for momentum. This is conservation of momentum. Now, there's a more elegant proof using calculus, because F equals ma, we've only dealt with constant acceleration for the most part, or if it's not constant.
Well, momentum isn't constant though.
And if acceleration is constant, it's simple enough to plug and chug like we've done. If acceleration isn't constant, you really should use calculus, but you don't end up with the exact same thing. Now, you might not have noticed this, but these are lowercase p's here. This is an uppercase p. Because my uppercase and lowercase p's really look the same, other than one's bigger than the other, you can't always tell with my handwriting if it's a big P or a little b. Traditionally in textbooks, the big case letter, the big P would represent the momentum of the system, and lowercase p is the momentum of the object in the system. However, I sometimes go by that and sometimes I don't. So if you see a p, it's momentum, and you can tell from the subscript whether it's the system or whether it is an individual object. a chance to catch up before I ask that question.
So, back on the whiteboard at the very bottom,
Right?
where it says MAVAF minus MAVAI,
Yep.
that's just change in P?
Yep.
A? Okay.
Yep.
And is that little P or big P?
Those are all, the only big P's are right here.
Okay.
Hey, marker.
And on the right side, negative MVBF,
Negative MB VBF
yeah, that thing,
plus.
plus MBVBI.
Yes.
One is plus, one is minus. So is that still just change?
It's the negative changes.
So negative change. Okay.
What is the momentum of this marker?
It's not moving. Or
Therefore, what is the
Zero.
momentum? Okay, in some unit. I let go of it. As it falls, is the momentum still zero?
No.
But I just went through this big bit of talking about how momentum is conserved. How is momentum conserved when it started when it had no momentum and then suddenly it has momentum?
The answer is it's not.
No,
I
momentum's-
hope.
Momentum is conserved, ignoring air resistance. What else had to have been moving?
The planet.
Yes,
Wait, seriously?
as the marker fell, the planet moved up. You didn't feel it?
No.
Huh?
The U?
But I'm insensitive. If I jumped off the table onto the ground, just to give us some sense of how far the Earth moves, it moves basically the size of a proton. So, not particularly noticeable. But if I'm looking at just the marker started out with no momentum, or had zero momentum, and then it started to have momentum. And so we can get into classification here of open systems versus closed systems. An open system is whatever I'm looking at, there's some outside influence. So if I'm looking at just the marker, if I'm looking at just the marker, there is an outside influence because the Earth is pulling down on it. So in an open system, momentum is not conserved because, well, there's an external force. And so in that case, we end up with the force acting on an object times time is going to be equal to the change in momentum. This right here has its own name. Well, actually, either one. It is known as,
Did you forget?
this is when I give my most obscure clue. When someone suddenly buys you flowers, that is called,
A gesture.
A gesture.
A nice thing. What is?
I get the impression that you're not up on your 70s perfume commercials.
No.
Impulse? Or
Impulse.
Dude, I haven't ever gotten perfume except for myself.
I haven't either, so not even for myself.
Ah,
But I've still seen the ad.
Okay, you're
And it is
also
available
older.
on YouTube. So when someone suddenly buys you flowers, that's called impulse. Impulse is also either the force times the amount of time or the change of momentum.
Okay, no change in momentum.
Now, if you were asked to find the impulse, which one do you use? Well, whichever one you have the information to find. If I give you mass, initial velocity, final velocity, I'm going to find the impulse using this. If I give you force and how much time it was applied, I'm going to use that. Either an I or a J is used for impulse. I'm going to use an I with a vector symbol over it. It is a vector. In a closed system, there is no outside influence. That should actually be a capital P officially. So in the marker, if I took into account the Earth, so I had the Earth marker system, they're interacting with each other. There's no outside influence because we're ignoring air resistance or any gravitational pull from any of us, or the sun, or the moon, or any other object, just Earth and marker. And in that case, momentum is conserved. Now, if I'm looking at this equation right here, the impulse equation, if I divide both sides by team, I get F is equal to the change in momentum over the change in time. Momentum is mass times velocity, so force which is the change in mass times velocity over the change in time, which is mass times the change in velocity over change in time, plus velocity times the change in mass over the change in time. This step right here, if you had calculus, would seem a little bit obvious using the product rule. If you have not had calculus, then just sort of let it flow. If the mass doesn't change, like we've had in pretty much all of our problems, if the mass doesn't change, we end up with mass times change in velocity or change in time, which is just acceleration. So we have F equals ma. If the mass does change, well, there's this extra term here which deals with how fast it's going and the rate at which the mass is being burned up or used. It turns out F equals ma is a specialized case. This is the more generalized case.
Dr. Fox.
So what kind of specialized case would it be?
The classic problem in physics is the rocket problem. Anything where the mass is being, the mass is changing at a continuous rate.
No, F equals ma.
F equals ma is when the mass doesn't change.
And the mass change. So that's
It can. If I have a rocket, I have rocket fuel that's being burned at a certain rate, the mass is changing as the rocket is moving.
For the closed
Isn't
system,
the,
Wait,
No.
am I wrong?
what did the O stand for in the closed system one on the last slide? Like, is that a 0?
That's a 0.
Just
Why is there a vector?
Because I have a vector on the left-hand side, I should have properly a vector on the right-hand side.
okay. Thank you.
It's called a 0 vector. It has a magnitude of 0 in a direction of
X. So conservation of momentum is both PF equals PI and also F equals change in P over change in T?
No, that's conservation of momentum right there. This is, in an open system, impulse is equal to the change in momentum, which then leads to this, which then leads to the next slide.
Oh, okay. Can you keep on this for a second then?
Do recognize the power of this. If I have two objects colliding in a closed system, the force that they exert on each other is going to change. If I have two objects that aren't touching and they collide into each other, they're going to exert a normal force on each other. So if that normal force gets exerted on each other, it goes from 0 to something, so obviously it's changing. It's going to peak, and matter of fact, if we did a force first time for two objects colliding, it's going to look kind of like a triangle, just having done the experiments enough. Not a perfect triangle, but close enough. Where it starts out with no contact, then it spikes, and then it goes back to they're either not touching anymore or they're going the same velocity.
In the open system, F delta T, is that a multiplication problem or a sum problem?
That's a multiplication problem.
Oh, then I put it wrong. That's why I was confused.
But what happens during the interaction from before, so you had it before, you have after, but what happens during the interaction, we don't care. This is the power of conservation momentum. From this, we can start to make predictions about what's going to happen in a collision. For example.
Is that a big P under closed system?
Yeah, it should be.
Okay. And what does the graph have to do with that?
It was indicating the fact that when two objects collide, that the force that they exert on each other is not constant.
Okay.
But it doesn't really matter what happens while they're colliding, before and after.
Okay.
We have two objects heading towards each other. It is a one-dimensional collision. One-dimensional, and they will stick together.
Can you go to the next slide on the blackboard?
In a collision where the two objects stick together, this is known as a perfectly inelastic